quantum reality what the math actually says in under 3 minutes. So the most reproduced experiment in physics reveals something disturbing. Reality behaves differently based on what information exists, not who's watching. When you fire electrons at a barrier with 2 slits, classical physics tells you to expect 2 brightly colored bands on the detector where the electrons pile up. It's not what happens though. Instead, you get interference stripes alternating bright and dark bands, the same pattern you'd see with waves interfering. Here's where it gets interesting. If you slow everything down and send 1 electron at a time, each electron arrives as a single dot on your detector, but if you wait long enough, these individual dots gradually build up to the same interference pattern. So you have single particles somehow creating wave statistics. The standard theory says that observation collapses the wave function, but that's not quite right. Here's what actually happens. If you place any mechanism that could in principle distinguish which slit the electron passes through, maybe a magnetic tag, a polarization filter, a detector that's switched off even, the interference pattern vanishes immediately. You just get 2 classical mounts. This isn't about consciousness then, or somebody watching. It's about whether the information exists in the physical world. The moment the universe contains which path information that you can look through, there's actually a clean mathematical relationship here. Visibility squared plus distinguishability squared has to be less than or equal to 1. It's actually gotten by Cauchy-Schwarz. So perfect path knowledge means 0 interference, and partial information gives you partial interference. The quantum eraser experiment drives this home. You can design things so that after detection, you choose whether to preserve or erase which path information. And when you sort your data accordingly and erase path information, interference patterns emerge. Within these sorted subsets, there's no time travel here. You just get revealing correlations that were always there. The fundamental point is that quantum mechanics gives you 2 different ways to calculate. When paths are indistinguishable, you add amplitudes and get interference. When they're distinguishable, you add probabilities and interference vanishes. In the next episode, we take this principle to macroscopic objects and ask why you never see interference patterns in cats.